Good morning, everybody. Welcome to episode 8 of AlgorithmsThread. I'm your host, David Hormeyer, and today we'll be talking about tree basics. So just as a heads up, this will be a little bit easier of an episode than most of them are, but I think it'll still be useful for people who are already familiar with trees and know what they're doing. And the reason for that is because I've put in a lot more time into this episode than I usually do, because I've created a custom set of 6 problems. I'm going to put it as a mashup on the Codeforces gym, so you can just go to the gym section. And then I haven't published it yet. I'll publish it when I publish the video, but it'll be in this gym section here. So you should be able to see it there. And it's a really good thing to practice. So if you think you understand the things in this video, to make sure you really are actually absorbing them, or if you're not interested in stuff that's this easy, you want to work on harder stuff, it's a good thing to speed run, and if there's anything that maybe you miss, this might be, watching the video might be a good reminder. All right, so this video, I'll have a link to it in this kind of still have a link to it in the description, and then also in the Codeforces blog post, and it'll be running for 2 weeks. So it's kind of the classic Ericto style version of there's some video lecture along with this set of problems. I'm not sure if I'll do this for future AlgorithmsThread videos because it was quite a bit of work. All 6 of these problems have unique flavor text. They're probably problems that have come up in other contests before, because a lot of them are fairly basic ideas. They're not too obfuscated like a lot of Codeforces problems are. They're more just to make sure you actually learn them, or learn the things that I'm teaching here. But yeah, it's I think it'll be very helpful for this video at least. All right, so another thing that was recommended that I talk about before I actually start going over brand new stuff are prerequisites. So what do you need to know in order to actually understand what I'm going to talk about here? There are 2 big things. The first is you have to know how to do a BFS and DFS. I'm not going to cover that because that would be way too introductory level, and it would be too slow for everybody else. But I'll publish some links in the description for other places that you can use to learn how to do that if you're not familiar with that already. And then also segment trees are really helpful for the thing I'm going to talk about at the very end of this video. So you don't need it for the first part, but at the end I'm going to say, yeah, and you can do this thing with a segment tree. And that's a very good thing to know ahead of time. So I'll also have a link to my segment tree video if you're interested in that, and that should be kind of enough to get you started as far as segment trees go. All right, so let's get on into the things I want to talk about. So the first thing is hopefully we all know what a tree is, but if we don't, I'll cover it really quickly. If you have some graph, which is a bunch of nodes, a bunch of edges, and let's say it's undirected for now, if the graph has n nodes and n minus 1 edges, then there are a couple interesting properties. The first one is, assuming it's connected, there are no cycles in the graph. So that's pretty obvious from just drawing this picture. But the reason it's true is we can add one more node and one more edge, and then we'll keep this idea of we have one fewer edge than we have nodes. So we can maintain this property that if you have n nodes and n minus 1 edges, you have no cycles. In order to have a cycle, you would have to have some extra edge. You'd have to add some edge, but you wouldn't add a corresponding node. And then in this example, you have exactly one cycle because you have one more edge, or you have the same number of edges and nodes. So this is the idea behind a tree. Now, there are a lot of things we can do with trees that we can't do with normal arrays, because we can abuse this property that if you're going from some node to some other node, there's only one path of doing it that doesn't revolve going down some node and coming back up that same edge, or down some edge, back up the same edge. So if we know we're going to do this, there's a unique path to get from one node to some other node, which makes a lot of the things we want to do with trees a lot easier. If you have some graph, the graph might be really complicated. There might be a whole bunch of nodes, a whole bunch of edges, and you don't really know which edges you need to consider. But here, the edges you need to consider, they're all connected kind of in a line, so it's easier to split things up. So that's why trees are really important and desirable for a lot of reasons. So let's talk about this first problem that I think is pretty interesting. So first I'll give the problem as a graph version. And then once we've talked about that, we can say, well, what if we have a tree instead? So here's just some graph. Maybe it's interesting, maybe not. We'll do something like that. And now what I'm going to ask you is, I want you to pick 2 nodes. So maybe you pick this node here and this node here. And I want those two nodes to be as far apart as possible. So the shortest path between them needs to be as long as possible. In this case, this looks like it's the optimal answer for this graph. The shortest path would probably be 1, 2, 3, 4, 5, 6 edges long. So the answer would be you can pick these two nodes and they're 6 apart. Now the question is, if I give you some big graph and I want you to find the farthest these can be, that's what your goal is. This is actually, if you want to solve this problem on some graph, I actually wrote a problem in the Brookfield Computer Programming Challenge. It's in the Codeforces gym. That's exactly this problem. Now, bounds are really small. I think n is less than or equal to like 100 or something. So the number of nodes is like less than or equal to 100. And what that lets you do is you can try all pairs. So you can say, well, if I started here and I traveled to this node, then, or you could say like if I started here and I traveled to every other node, in order to see the shortest distance from this node to every other node, if all the edges are unweighted, we can do a BFS from this node. And we would have to do that from every possible node because we don't really know where this path is going to end, or where it's going to start, where it's going to end. But if we know what the start point is, then we can find the best endpoint. So the runtime there would be the number of edges, or number of nodes times the number of edges. That's the runtime of your BFS is the number of edges. So the total runtime would be that, which in this case would be about n cubed. You could also do Floyd-Warshalls, which would do a similar thing. So that's the problem for a graph, and it turns out if you just have some general graph, if you don't have anything that you can notice about the graph, if it's just like some completely arbitrary graph, you can't really do much better than doing a BFS from each node. Which means if you ever have some programming problem, and this is the subproblem you have to solve, maybe you've like simplified it in some way. You're like, okay, if I can solve this problem, then I can solve the real problem. Well, if the problem you have to solve is find the diameter of this graph, that's a very difficult thing to do, which probably means that you've made some simplification where you've lost important information about the problem. So there have been problems where if you can find the diameter of a graph quickly, right, like if n was like 10 to the 5th instead of 100, if somehow you could do that, and like m is also around like 2 times 10 to the 5th or something. If you can find the longest path in that graph under no restrictions about the graph, then you could solve the problem. Well, that's great and all, but you're probably not going to be able to do that because a lot of really smart people have spent a long time thinking about it and haven't gotten very far. So that probably means in your simplification of the problem to this version, you've probably oversimplified in some way that's not super helpful. All right, so there's that. But now the question is, what if instead of it just being a general graph, what if it's a tree? That makes it a lot easier, and there's this really cool, really simple algorithm that you might know already, which will do this for you. So let's draw some tree like this. Basically, all this problem is we need to find the diameter of this tree. So it's a common problem. Maybe the idea is pretty simple. Here's what we're going to do. First, we pick some arbitrary starting node. Maybe it's this one here. And now the first thing we do is we find the farthest node from this starting node. So we can do a BFS from this. That takes like order n time because it's a tree. It has order n nodes, order n edges. We do some BFS, we find the farthest node. I think it would be this node. I won't actually find all the distances, but this looks like it would be the farthest node. So now we have this red node here. One really important aspect that's a good thing to consider is that we know this is going to be the end point of some diameter of the tree. So one of these longest paths will end at this node. That's not necessarily true for graphs, but it is true for trees. Once we have this endpoint, we can just do a BFS from this node, see, all right, what's the farthest node from this node? We'll probably get this one maybe. And now we can tell, all right, the diameter of this tree is this path right here. So I mentioned this doesn't necessarily work for graphs. Why not? Well, let's imagine we have some graph that looks like this. It's just a really big loop. And then maybe it's got one extra node over like this. So since we have this loop, that introduces additional challenges that we wouldn't have on the tree. Maybe if we start our BFS here, the farthest node that we would find would be this node here. But neither of these nodes are actually part of the diameter. The diameter of the tree would be this, like that. And we would miss that entirely. It's very difficult to find unless we have some information that we can use on this graph that makes it not just a general graph. All right, so that's the first idea, which is finding the diameter of a tree. Now, this is also like you might be like saying, okay, I know how to find the diameter of a tree. I didn't start programming last week. Like, that's a pretty basic thing. But you can use it for other ideas that are maybe a bit more helpful. And here's one of the observations you can make if you have the diameter of the tree. So say you know this is the diameter. These, these 5 nodes, or 6 nodes and 5 edges. What you can do is you can draw out the diameter in a line. So imagine you stretch out the tree by the diameter. Now you have subtrees from each of these nodes, and they might do different things. But we can, like, if the tree isn't rooted in some way, then we can like make these subtrees in interesting ways. But there's a really important property that we can do if we draw it out like this, which is the height of this subtree is at most 1. The reason for that is if it were greater than 1, this node here wouldn't actually be part of the diameter. For the same reason, this has a height of at most 2. This also has a height of at most 2. This has a height of at most 1. And then this has a height of 0. Same thing with this here. So yeah, that's like a useful property. It might be helpful to think of. The other thing is this isn't only true for diameters. There are other times when looking at a tree like this is really helpful. A couple examples are Monaghan's snake on a tree, I think it's called. That's one of them. Also, Facebook Hacker Cup qualification round problem D2, quite a mouthful of a problem. But that problem also, for me at least, I thought it was very helpful to imagine stretching out some important path on the tree, and then considering subtrees rooted at each of the nodes along this path. So that's like another idea that's really helpful. How exactly it's useful depends on the problem, so I'm not going to spend too much time talking about this by itself, but it is like a useful way of like imagining decomposing the graph into a bunch of nodes on some path, and then all the subtrees that come off of those. All right, so let's move on to the second main idea that I want to talk about today, and that is binary lifting. So one of the problems in the problem set, I made a meme sort of thing about binary lifting. And it's binary lifting, like the idea is a really important idea. And I think it's also something that isn't really very commonly taught at all. And if you don't hear about it, it's like maybe not super easy to find out about. So this is like one of the main reasons that I'm prioritizing talking about it, because I think there's a lot you can do with it. And it solves lots of very useful problems, and it's not like it should be a beginner topic, but a lot of times I think maybe it's not. So let's say we've got some tree, and there are a bunch of problems we might need to solve. But the general idea is if we start at some node, and we go up some number of nodes, we want to see basically what happens, right? So maybe we want to ask questions about like, what's the min? If we go up some number of nodes, what's the minimum value there? Maybe we just want to ask what node do we end up on if we go up some number of nodes. If we go up 5 nodes, where do we end up? Yeah, so we can answer different questions like that, and we can do all of those using binary lifting. We can also do some other stuff too, so I'll talk about that in a bit. But let's talk about the general idea of what binary lifting is, and then how we can use it to answer those questions. So the general idea is we're going to store for each power of 2, we're going to store what happens if you go up that power of 2. We're going to do this for every node as well. So we have n nodes, and then we have log n powers of 2 that are relevant. So the total number of things we're going to store is n log n. Now, if we imagine like what happens if you just go up one node. Well, that's a really easy question to answer. I'll just draw them for things in this path, but you can imagine for every node, we can just say, what is the parent of this node? We can figure all of that out in a DFS. So we can DFS, we'd go down all of the white edges that I've drawn here. We can just store for each node what's its parent. That's easy to do. All right, now on from that, we want to figure out what happens if you go up 2 nodes. So here we know how to go up 1 node, but to go up 2 nodes, you just go up, you follow your parent and then you follow his parent. And that's true for all of the nodes. So for every node here, I won't draw them all in because it'll get kind of messy, but for every node, we can store what happens if you go up 2 nodes. Then to store going up 4 nodes, it's the same thing. You just go up, instead of taking your parent twice, you take what happens if you go up 2 nodes twice. So going up 4 nodes is the same as just going up 2 nodes 2 times. So then we have this path here. By doing this, we can really easily, it's just like a matter of like 2 for loops and an if statement, find out what happens if you, from each node, if you go up each possible power of 2. So basically what the pseudocode looks like is like for the exponent is equal to 1 all the way up to like 20. And then for each node, now if you can go up like node.lift at this exponent minus 1, if this is not equal to null, then you can set the, well, we'll just commit to this fully here, right? So then node.lift at this exponent is just going to be equal to the node.lift at the exponent minus 1. And then on top of that, we want to go up again at the exponent minus 1. So that's kind of the pseudocode. So what's important to notice here, this is assuming we've already set the lift at exponent at 0, because that's just setting the parent for each node. So that's an easy thing to do. But we'll set these in the order of the exponents, so we hit this in the right order, and it's really easy to code. This is all you need to do in order to compute this binary lifting table. Now this is just if you want to store what node are you at if you go up some power of 2. We also might want to consider other things, like not just what node are you at, but also let's consider something along the edges that you go up. So in this case, we just stored, all right, if we go up these nodes, what are our values? But it's possible these edges have some sort of weights or something. Maybe it's like 3, 5, 1, something like that. We might want to know, all right, if you go up some number of edges, what is like the sum of these edges, for instance? And we can just look at the sum of this edge here. We can make another table. This is for going up some number of nodes. We can also make some table for what would the sum be if you go up this power of 2. And we can just look at the 2 corresponding entries in that table to figure out what the sum would be if we go up by a bigger power of 2. So there are lots of really useful things you can use this for. One of them is if you have some tree, maybe you've got some tree like this, if you start at some node and I ask you to go up by 10 nodes, right? So we want to go up 10 nodes. If we just walk naively, that would take linear time, because this number might be really big and the tree might be really long, might be pretty much just a rope. So if that's the case, then it's like, well, there's not really a good way of handling that other than just walking up naively if we don't have this binary lifting. Once we have this binary lifting, we can repeatedly take the biggest power of 2, less than 10, and we can split 10 up into just numbers that are powers of 2. So in this case, 10 is just 8 plus 2, which is 2 to the 3 plus 2 to the 1. So we would take 2 to the 3 steps up, then take 2 to the 1 steps up, or you could do it in the other order, doesn't really matter. But in the same way that you can take some number to some really big power by doing binary exponentiation, you can do binary lifting in order to take some number of steps up once we have these powers of 2 computed. All right, so there's that idea. We can take any number of steps up. That's a helpful thing to notice. The other thing we can do is we can say, what is the closest node that's an ancestor of 2 different nodes? So maybe I give you these 2 nodes here, and I ask, what is the first node, like if you go up from both of these, what is the first node that's a parent of both? That's called, it's this one here in this example, but it's called the lowest common ancestor. My spelling on ancestor might not be perfect. I'm not a spelling bee champion, but I think it's pretty close at least. So yeah, this is also often called LCA. Now in order to do this, we pretty much do the same thing as we did before. The first is we want to make sure we're comparing 2 nodes that are on the same depth. So we can store the depth of each node in our DFS, right? This node has depth 0. When we go down this DFS, we increment the depth. So this is depth 1, When we go down the DFS again, we increment it. This is depth 2. We can sort it for all the nodes. Now, if these two have different depths, we want to go up some number of spaces so that we're comparing nodes that are on the same level. So now, instead of comparing these two nodes, we'll be comparing... I erase some of my red lines. We'll be comparing this node here and this node here. Now, if these are already the same node, it's a very easy problem. If they're the same node, we just return that node. That might happen if we initially start comparing these two nodes here. We want them to be on the same depth, so we move this one up. We move it up by 3. We can do that in log n time. And now we're at this node here. So that works. And in that case, if they're the same, we want to return. But what if they're different? Well, then we can pretty much do the same idea as kind of like binary searching, how far up we should go. So we have a bunch of pointers for this node. I'm going to erase all of these red arrows and draw in just the ones that are relevant here. So I think we'll just have 3 because the graph is pretty small, but we can go up 1, we can go up by 2, or we can go up by 4. Then we have other pointers for this node as well. So we've already special cased what happens if these two nodes are the same, then we can just return this node. We can also special case if these nodes are different and their parents are the same, that means we want to return their parent. In all other cases, we know there's some power of 2, where if we take that many steps up, then we'll be at the same node for both of these. If both of these nodes take 4 steps up, they'll be at the same node. Even if it's different, if they both take like 2 to the 20 steps up, right? That's a very big number. It's about 1 million. If they both take 1 million steps up, they'll both have passed this root. They'll both be in null land here. So this is like null, right? If they take a lot of steps up, they'll both be here. So there's some point in which it goes from we're at the same node, or it goes from being at different nodes for powers of 2, and then at some point we're at the same node. What we want to do is take the biggest step possible that we can in order to be at different nodes still. So in this case, both of these will take this path here, and then we can recursively find the lowest common ancestor on these two nodes. Now, we can speed it up a little bit. If we just did this naively, I think it would be log squared, but it might be just log n. We can make it a little bit faster by saying, well, the biggest jump edge we have to check in the future now is only of size 1. It's not of size 20, right? We don't have to try and jump up 2 to the 20. We just have to jump up by 2 to the 0. Because we know if we take any bigger number of steps, we'll be at the same node. If we just go up, that's still going to be true. So that's the idea behind finding the lowest common ancestor. So we just keep doing that until we have 2 nodes that are different and have the same parent, or until we hit 2 nodes that are the same. Awesome. So if that's like a new thing to you, there's a really good way of practicing that, which is just solving problems that require it. And a good thing you can do with that is just solve the problems that I made for the gym set. Okay, the last thing I want to mention really quickly is if you're able to find the lowest common ancestor, and you've also calculated the depths for each of the nodes, that lets you do one more thing, which is find the distance between 2 nodes in a tree very quickly, in log n time. You can actually do it even better. You can do it in order 1. You can do that with RMQs, which is in my RMQ video. But here's the idea for log n time. If you can find this LCA in log n, like we just talked about. Once you have that, you know the distance is going to be the length of this path plus the length of this path here. In other words, we can split this up into 2 separate edge groups, where like each edge group goes from some node to some ancestor of that node. And now we can also easily calculate the length of this path here, because if this is like depth, well, let's see, what is this? 0, 1, 2, 3, 4. This is also depth 2, depth 3. So the total length of this blue path will be 4 minus 1 plus 3 minus 1. So it's the depth of each of these original nodes minus 2 times the depth of the LCA. It's important to not forget the times 2. That's like a common mistake that I made when I was first starting out, and I've seen other people make as well. So it's like the depth of one plus the depth of the other minus 2 times the depth of the LCA. Yeah, all right, very cool. So that's the idea behind binary lifting and LCA. And there's one more thing that I still would like to talk about, which is kind of pretty much completely different, but it's another very useful skill that's like super important and maybe a bit difficult to learn. So here's the idea. Imagine you have some tree. It can be pretty much any tree you'd like. And we'll say for simplicity, we'll say it's rooted. Now, if it's not rooted, you can pick an arbitrary root and then do something with that. But yeah, we'll just make it rooted. So we'll say this is the root. Now, one problem you might use this for is like, suppose that you want to answer some information about some subtree, or maybe you want to update every node in some subtree. So you want to do something like that. Well, that might be a tricky thing to ask you to do because initially it seems like there might be order n nodes in a subtree, and they're kind of like, they're all connected maybe, but it's not easy to think about how you might be able to do a whole bunch of, like, access a whole bunch of nodes all at once. Now, this is the part that's really important to know segment trees for. If you're not familiar with segment trees, you should definitely go learn that first. But if you are, there's a really nice way we can apply segment trees to the idea of a tree. So how do you do that? Okay, so one really important thing to understand is a segment tree isn't a tree. I guess it kind of is a tree, but it doesn't operate on a tree. A segment tree operates on an array. Segment trees can do things on some range of an array. Can't really do things on like parts of a tree. So when we have some array like this, we can build a segment tree by splitting things up into halves like this. We keep splitting each half into sub-halves. And we just keep doing that so that you can represent any range in log n segment tree nodes. Now, what we want to do is we want to convert this tree here into an array. And then once we have this array, we're going to convert the array back into a tree, but this time it's a segment tree. And since the segment tree is balanced, we can make everything be log time instead of linear time. So basically we have this tree, we turn it into this array, and now we turn it into a segment tree, which is like beneficial for other reasons. So that's the idea. We go tree to array to tree again. So now this part is very easy. This part is just like, this is just what segment trees are. And hopefully I've made everything in this video seem pretty easy. That's the goal. It should all seem basic, which means I'm not explaining things that are too confusing, but we'll get into harder stuff in future videos as well. So don't worry about that. But the interesting part is, how do we do this step on top? How do we go from some tree to some array? Well, here's the idea. This was in the initial picture on the thumbnail. And that is, we're going to go through the tree in this order. When we do this, we'll hit every node some number of times. But the interesting version, like we'll take this path here, the interesting version will be the first and the last time that we hit each node. So there are a couple different ways of doing this, but the first way that I'll talk about is we're going to increment a counter every time we go down an edge. And then we're going to store what is the counter when we enter some node and when we leave that node. So I'll just draw this out as an example for this tree here. And then that should give a pretty good idea of how it works. So initially the counter for this node is 0. Then we go down this edge, so we increment the counter. So now our counter is at 1. Now we'll be at this node here. And the counter when we enter the node is 1. So now we go down this first edge here. And the counter when we enter it is now going to be 2. So all of this is happening in a DFS, by the way. We just do some DFS and we store some counter when we go down the edge. We also return what the counter is when we finish that DFS. All right, so now we're at this node. It doesn't have any children, which means it doesn't actually increment the counter or DFS anywhere from them, and it just returns. So it sets the counter to 2 when it returns. Now we're back in this node, and we still want to finish our DFS. We just traveled along this edge. Now we want to travel along this edge as well. So we increment this counter, now it's 3. We keep doing the same thing. Now this counter will be 4. We leave at 4. We go down this edge here. So the counter is now 5, stops at 5, stops at 5, stops at 5. Down this counter, it starts at 6. This is 7, stops at 7, 8, 9, 9, 10, 10, 10, 10, and 10. So there are a couple interesting things that we've done here. They're not immediately obvious, but once I say them, they should be obvious. The first one is the number that each node starts with, the number that we were at when we entered each node, is going to be different for every node. Every node has a different number. They're all unique. So we can order all of the nodes by whatever the number was when we came into that node, which means the root will be node 0 now. This node will be node 1 in this DFS. This node will be node 2, etc. The other thing is, what's really nice is when we look at this path, if we're interested in some subtree, that subtree is now a continuous range of nodes, which means if we order these nodes in some array by that first number, all of the nodes in this subtree will be adjacent in the array. This will be 1, 2, 3, 4, and 5. They'll all be next to each other in the array. They'll be these positions here. That means if we want to do something to the subtree, maybe we want to find the sum of the values on all nodes in the subtree. All that is a range sum on this array. If we want to find the minimum of all the values, that's just a range min sum, or a range min, on a segment tree. And to make things even easier, we know for each node, we know the first node in it and the last node in it. So if we are looking at this node here, what that range is really easy to find. It's just from element 1 to element 5, inclusive. And that's it. So we can really easily do operations on subtrees. Anything we can do on a segment tree, we can do on a subtree. Also, if we want to do modifications, we can do those on a segment tree too. So if we want to update some node, we could do that pretty easily. Also, if we want to update some entire subtree, we could also do that. So with lazy propagation, segment trees can do range set 2, or they could do like range add, for instance, or like range flip, maybe. So all of those things are things that you can do with a segment tree. Now, since we've converted this tree into pretty much an array, we can do those same things on the tree as well. Okay, there's one other thing you can do, which is kind of interesting. It can't do all of the operations that this can do. So this is only for subtrees, but you can also do some slightly interesting things with paths as well. So I'll draw a new tree here, and here's the idea. We're going to do this counting in a slightly different way. So again, we'll have the same sort of path. This path is usually called an Euler tour, which does not start with the letters O-I-L, even though it's pronounced oil. It starts with the letters E-U-L. Euler tour. Go figure. I guess it's just some guy's name. That's how he wanted people to pronounce it. Or I guess that's how it's pronounced, not how he wanted people to. It doesn't matter how people wanted to pronounce it. It's just, that's the truth. But yeah, you've got this path here. Now, what we'll do is we'll update on both when we enter the node and when we leave the node. So now each node will have 2 positions in the array rather than 1. It's pretty simple how to do this as well. You just increment the counter in 2 places now instead of 1. So now we have something that looks like this. All right, so now I said you increment the counter in 2 places, but what this lets us do is we can now do some sort of path query that's kind of interesting. For instance, let's say we want to query like the sum along a path. So the sum of like values at certain nodes, if we give each node a value, we want to say what's the sum along some path. Now, you can do this with HLD and some other stuff as well, but you can also do this just with this trick, which I think is pretty nice. And here's the general idea for that. we're going to label the value of some node in two places, once as a positive number, once as a negative number. So here we'll have some positive number. Here we'll have some negative version of that same number. Positive version here, negative version here. So if this number on this node were 3, we would have a plus 3 on this position in the array, minus 3 on this position in the array. This would be, if this were like a 1, be plus 1, minus 1. Again, we have a positive version and a negative version, and a positive version and a negative version. So now the interesting thing is, if we want some path like this, these subtrees that we're not part of get canceled out. If we look at this subtree here, this positive and the negative of the same value will cancel each other out. So if we want to find the sum from this root node to this node here, we can find the sum along this path, and only nodes that we have entered but haven't left yet will be the things we're taking the sum of. That'll be all ancestors of this node here. So now we've converted some path query into just a range sum. Now you can do this for some operations, but not all. For instance, you can't do min along a path using this trick. For min along a path, you'd have to do something else. Maybe HLD, maybe something else. If you're not doing updates, you might be able to do binary lifting. But yeah, there are different things you can do. But if you're doing something that's undoable, so for instance, if you want the XOR along a path, or maybe you want like the sum or the product or something like that, product under mod, then those are all operations that you can undo. So this allows you to do the operation, this allows you to undo the operation. If you have something like that, then this trick sort of works. All right, so those are the 3 things I wanted to talk about. Maybe it was a little easy, but if it is a little easy, then you should have no trouble at all speed running these problems. So I hope you enjoy them. Let me know if you find this new format particularly helpful. If not, it's a lot easier for me to make these videos if I'm not making these practice problems, because making these practice problems took a very long time, and recording this just took a little bit of time for me to make notes and plan what I'm going to talk about, but like the actual recording part wasn't that hard, whereas I spent pretty much all last week making these problems and then making data for them and stuff like that. So yeah, let me know if it's helpful. If it is helpful and like this is what high quality learning materials, like this is the best way to do it, then by all means I'll keep doing it. It'll just result in like less tutorials per unit time, because like this is where a lot of the time is going. Yeah, that's all. So good luck solving the problems. I hope you enjoy them, or at least try them, because I put a lot of work into them, so I hope you like them as well. They were tested, so there shouldn't be any bugs. If there are, feel free to let me know. If you're like, I am very sure my solution's right and the data is wrong, then you can like post in the comments of the blog. If you have any questions on anything I talked about, the comment of the Code Forces blog is definitely the place to ask. If you ask in the comment of the YouTube videos, you might get an answer from someone, but you almost definitely will if you ask in the Code Forces blog. Yeah, that's all from me. I hope you enjoyed the video, and I hope you're having a great day. We'll be back to harder stuff next time. Thanks for watching, and goodbye.